I mean, it will wobble afterwards. That's why I wobbled. Okay. As I just mentioned, we will look at the canonical diffraction problem, which is pictured on a cover of a Russian print of Nobel book. But of course, since I'm from Moscow State University, I don't call this problem Nobel problem. This problem was solved by some Russian scientist. His name is Lev Weinstein. I will call it Weinstein problem. And to be honest, I don't know who was the first, because Nobel, he didn't solve anything. Everything was solved by Jones and people before him. But they were, like, both of them, Weinstein and Jones, they were active at the same period of time. Probably they did it simultaneously. So, point 3. Diffraction by an open element plane waveguide. Which is known as Weinstein's but you know, it's a good Weinstein, not bad Weinstein. So as usual, we start from statement. For statement, we have two parallel half planes. Origin here at this point. For some reason I use small h as width of this waveguide. What else do I have? I have a plane wave coming from infinity onto this waveguide. And Neumann boundary conditions. Of course, I can go Dirichlet once in the same way. But for acoustics, it makes sense to consider now. And okay, what else we need for the statement to be complete? As we said, we have an incident wave, so our field is presented as a sum of scattered of incident wave. Then, it should satisfy Waveguides equation, and we have mixture and radiation of course, we can look at this problem as one step more complicated than half plane problem. So we had one half plane and we added second one. This is basically what we do with India. Did with India for some time. This is, but technically, actually, you need to do much more computations to solve it. It's like from a technical point of view, it's much more involved problem, and I won't be able to obtain a solution today. But I will state a problem. I will show that this problem is a scalar linear Hopf problem because we can obtain a matrix problem. Who knows? And then you probably know already enough to obtain solution yourself. And the technique, and I will use a similar technique to derive linear Hopf equation. And I hope you remember how I did it for the half-plane problem. I used Green's theorem, Green's identity. Do you remember it? At some level. Good. But, okay. I will omit some bits, but you will tell me whether you understand what's happening, and then we will discuss them if not. So, I will introduce an auxiliary function, and this auxiliary function is just plane wave, and this bit will give us exponent for Fourier transform when this bit is 0. And this thing will act as a spectral parameter for our linear Hopf equation. And then I will apply Green's identity with W and scattered field. But I will apply the identity for 4 different domains. This is the first reason why things are more involved right now. Okay, let's draw the first domain. Let's write domain 1. And in domain 1, I have my waveguide, and I just consider upper half plane. And I will write something like this, and I hope it will be clear to you what I mean. And let's write its identity. So my Green's identity. So this is omega 1, and I have a function, an outgoing plane wave B. And I apply Green's identity to the boundary of this domain. And of course, due to radiation conditions and decaying of the outgoing wave, the integral on the big arc tends to 0. So I basically have exponential decay in all directions. And then I just have an integral going from minus infinity to plus infinity. Then I will be getting just some half-line Fourier transform, and this thing corresponds to the half-line Fourier transform of the field for this bit. And this thing will correspond to the half-line of Fourier transform of the normal derivative of the field. And here, of course, I also have boundary conditions, which I also should take into account. So this is a Fourier transform of the normal derivative of the field, but that actually works as a forcing, because this bit is equal just to the normal derivative of the plane wave, and we know what the plane wave is. And okay. Well, if I put the things I've said on the paper, it will mean the following. This term comes from differentiation of this thing, so this is just this term. I have minus, because probably I was writing it like this, so this will be a correct version. Since it's 0 on the right, it doesn't matter. And here I also use a lower index U plus, because I consider a field on this side of the half plane. So I have field defined here and here, and they're different. So this is a limit from above. And this thing is 0. And this thing is definitely a Wiener-Hopf type of functional equation. This thing has actually 3 unknowns, and this thing is known because it can be expressed in terms of the plane wave. So I will put this thing as forcing. Highlight it. To make things more clear for you, I will write down the definitions, so you'll be able to check if you want to. Here, that's how I denote the limit from left. And of course this thing just some pole. If I integrate it, take limits, I will have a sine minus k cosine theta. Right? Okay, that's one equation. Let's obtain 4 more. And I will probably skip the derivation of equations, but I will show you the domains to which these equations should be applied to. So this is domain 2. And as you see, I take our auxiliary function reflected. So now I again have exponential decay in infinity, so I have minus 1. And this is domain 2. Let's draw domain 3. For domain 3, domain 3 is just this half plane, but now I need to shift my plane wave. So if I take it like this, it will give me an exponential factor here, and I will have Fourier transform here. And finally, for domain 4, was it okay? Were you able? You are not able. I can reach it. It's not hard. Let me know when you are finished. Probably you can guess the force. choose an outgoing wave. For example, like this. And if you do it, you will have three more equations like this. And then it's kind of, if you study, then you will find that you can reduce them just to a system of two equations. That's something which is quite obvious. And eventually, after I will spare use algebra, the final result looks like 2 times 2 matrix VH linear form equation. Here, similarly to what we had before, psi minus and psi plus are some unknown vector functions, but we know that this thing is analytical in lower half plane and this thing is analytic in upper half plane. K is known matrix function which is referred to as kernel of linear form equation, and this is also a known forcing term. And okay, I will write them down. Phi minus is composed of V minus theta minus, which we are about to define, and C plus is composed of U plus and Phi plus. So here I define, we already know what is V plus, we know what is U plus, and to write what is U. Let me do it. I think it's a jump of the field on the lower half plane. It's a spectrum of a jump. So here I have I put plus on top, meaning that I take a limit from above. And for U plus, it's also a jump. I will write it like this. The field on the upper half plane. This is spectrum of light. Derivative. The most interesting bit the kernel, and if we know how to factorize the kernel, we know how to solve the problem. So by default, if we have a matrix with a Hopf equation, we've got a lot of problems. Because we don't know how to solve matrix with Hopf equations, it's still an open problem, and if you feel, young and ambitious, you should solve it. But those who feel old, don't have any ambitions left, they say it's a dead end. Dead end, it's nothing we can do about it. But to be honest, we don't know. Also, this thing has kind of two problems at the first glance. First of all, it's matrix. Second, it has exponential growth. And if we have an analytic function but exponential, we cannot apply Liouville theorem. That's a problem. So we need to factorize it, but also we need to factorize it that way that we don't have an exponential growth. Because this thing is kind of like, if we were naive people, we said, okay, fine, this thing is analytic everywhere. Because it's an exponent is like an entire function. It just has exponential growth at infinity. And then we just factorize this term, we think we won. But unfortunately, that's not the case, but I will show that this matrix can be reduced to a scalar meaningful problem. And for completeness, let's write down and this is a pole which corresponds to the incident plane wave, the same thing we had for half-plane problem. So what I will do is I will show that we can reduce the system of two coupled equations to just two scalar linear equations. And of course we could have done it earlier if we just symmetrized our problem, but I will show you a brutal approach when you just don't want to think. Apply linear algebra. So, an easy thing to do. Let's make let's build a canonical form for this matrix. So do an eigenvector decomposition and present it as a product. I did it. Of course, I should be able to do it by hands, but these days I use Mathematica, even for such simple things. Mathematica told me. So what's nice about this decomposition? That our eigenvector matrices, diagonalizing matrices, they are constant. And we can multiply our equations by these matrices. And these matrices will not spoil the analyticity of our functions. And then I say, let's introduce new variables. Say minus and same thing. Say plus and for brevity, the same notation for sync term. And then we have an equation. This is just two separate scalar equations because we don't have any non-diagonal terms. So I can just write it as two scalar equations and solve them each separately. And of course, another thing to come to the scalar equation is just, here this thing or like this thing gives us an antisymmetric part of the field, and this thing gives a symmetric part of the field. And we could have symmetrized and anti-symmetrized our problem from the beginning, and then we would arrive to scalar problem by default. And what I will say next, okay, we already know Wiener-Hoff method. Now we can apply standard technique like Cauchy integral or whatever we want. Open Noble book. Actually, this problem is solved in Noble book since it's on a cover in a Noble book. And you can see how this problem is solved. Or you can try it yourself, and as I will give you like a theoretical homework. So it's not necessary to do, but if we do it, we will learn some funny stuff. But probably it would be very hard for you to do it just yourself. You probably should consult with Noble. It's quite challenging to do it nicely. So, homework. Yeah, this gamma, yeah, I think I put gamma in the square root. So this is gamma. I think I've put it before. Okay, homework. Factorize. Function of x into a product of functions analytic lower and upper half plane, and f of psi is k square minus psi square 1 plus minus as I said, if we allow exponential growth, the factorization is trivial. We just factorize this term, which we already did for half-plane problem. But we need to factorize this term, and we need to factorize it in a way that it doesn't have an exponential growth, so it grows only polynomially. So try. Maybe you can guess how to do it yourself, but there is only one way to find out. You should attempt. So, and the last bit I want to talk today is speculations. I will speculate about solutions I didn't obtain, but if you go all the way down, you construct a solution, then you need to study it asymptotically the way we did, for example, for diffraction by cylinder. So, and once you study it asymptotically, you will find quite a few surprising results. And one of them which I didn't check, and I'm starting to doubt. So you should check and tell me whether it's truth or lies. I think it should be true. So when we have a waves coming on a waveguide, most of them will be reflected very well by this open end. But if we send a wave at a grazing incidence, this wave almost completely will go into the waveguide. I'm not sure. This is one funny thing, and this thing should follow just from the result solution. And vice versa, we can consider a different problem. We can consider a radiation problem of the open wave and of the waveguide. And if we consider radiation problem, so we have for radiation problem, we have our we consider a mode close to cutoff. I'm failing it, but you should understand. Let this mode be close to cutoff. And if you just have a solution, of course, first you need to formulate the Wiener-Hoff problem. This is homework to formulate pH problem for this radiation by an open-end waveguide. So we have a node which propagates from left to right, and it radiates something outside of the waveguide. First, we can formulate it as a Wiener-Hoff problem almost similarly to what we did to the incident half plane, and the difference only will be in the forcing term. You will get another forcing term, but the kernel will stay the same, which makes sense because we just change the forcing term in our Gilbert equation. And if we consider this mode, we will find out that once it reaches here, it almost completely reflects back and goes back with coefficient of reflection close to -1 approximately. If the mode is close to cutoff, and this is actually an amazing result. Also, I need to say this is homework with a bit complicated. If you will be able to solve it and show this thing, then you're as smart as Einstein or Jones. And like, I need to mention myself, my PhD thesis was like this problem, when you have unequal widths, and I had a lot of time trying to show the same for unequal widths of half planes. Let's go shift it. And what? Staggered, yeah. So smart people from UK say staggered. Yeah, that's how it's in David Abraham's paper. So this problem is, both of them are very well stated, so you can, if you're curious, you can look at the solution. And the physical application of this thing is that if we have not a waveguide, but a resonator, a parallel plate resonator for pre-piro resonator. And we send a mode close to cutoff. This mode will not escape the resonator. So it will reflect with the coefficient -1 here and -1 here, and this resonator will have a very, very high Q factor. Of course, if we compute a sum, it will give us just some standing wave. And this is one way to feed the energy to like optic rays, like lasers and something like this. And you can find all these results just from not just by solving the corresponding to the problem I showed you today, which is amazing idea. Look, and this is, as I said, it is known as Weinstein problem. That's probably the second common example of the success of Wiener-Hopf method in diffraction theory. That's it. Questions? Good. So, like, subscribe, share, and hit the bell.